Welcome to the physics department's virtual graduate student visit. We hope you're doing well. I'm John Sarf, one of the faculty members in the plasma physics group.
And I'm Jeff Parker, another faculty member in the plasma physics group.
So we'd like to take this opportunity to tell you a little bit about the plasma physics program in our group. When I do this in person, I sometimes start with making sure that people understand what the context of plasma is. So if we're in a room, maybe there's some fluorescent lights on and the lighting above you, and I'd look up and I'd say, there are 40 plasmas on right now in this room, just to make sure everyone understands we're talking about ionized gas. So plasma is the fourth state of matter. If you continue to add energy to a gas, eventually there's enough average energy in the particle motion to ionize. So that's the plasma state of matter. It's the most common state of matter in the universe. So what we study here at Wisconsin is plasma physics. How do plasmas work? We have a guiding theme, however, which is to understand how plasmas interact with magnetic fields. This is important both in natural plasmas, and it's also important in achieving fusion energy as a limitless energy source here on Earth by using the magnetic field to provide insulation to keep the plasma hot. What you're looking at the moment across a backdrop, which is a cartoon-like picture of the sun, obviously on the left, and you can't quite see it, but it's the Earth on the right and its magnetosphere. And the sun, of course, is our nearest large source of plasma. Plasma streams from the sun, we call that solar wind. It impinges on the Earth, gets trapped in the Earth's magnetic field. The part of this plasma which reaches into the atmosphere and causes the auroras, the northern and southern lights. This is something that you're familiar with. The pictures that you're looking at are representative of our program. So they're pictures of some experimental devices, which we'll be discussing, but also some pictures of other contexts. ITER is shown here. ITER is the next step in fusion. And so it represents our interest in fusion energy and our connections to collaborations in fusion, both here in the US and worldwide. We also have a strong theory and computational program. And we also have an engagement in important missions, which are sampling the plasma right now. The magnetospheric multi-scale mission is a set of 4 satellites which are circulating around the Earth, sampling the plasma in the magnetosphere to understand how this plasma, which is originating from the sun, interacts with the Earth's atmosphere. So what we'll do is we'll just go through this and talk a little bit about our program. The first thing that we'd like to do is show you the faces of who we are. So this is the plasma faculty in the physics department. There are 7 of us. We're a relatively large group in the physics department. In addition to ourselves, the faculty members, we have full-time scientists working with us. We also have engineering staff, postdocs, and undergraduates who work with us. And of course, graduate students, which is the context for our discussion with you. So the people listed here are Stas Boldarev on the left. He's a theorist. Jan Egdahl, experimentalist. Carrie Forrest, an experimentalist. Jeff, who you'll hear from in a little bit, is a theorist. Myself, I'm an experimentalist. Paul Terry is a theorist. And Ellen Zweibel is a theorist who has a joint appointment with astronomy. We have a large program at UW, and some of our colleagues who are faculty colleagues here on campus are affiliated with us. 4 of them are listed here. And I'll talk about the larger program a little bit at the end of this presentation, the last part of this presentation. What I'd like to do first, and then I turn it over to Jeff to talk about the theory program, is to show you and talk about the experimental program, starting with what we call the Wisconsin Plasma Physics Laboratory, or WPL. This is a relatively new user facility, quasi-user facility funded by the US Department of Energy and the Office of Fusion Energy Sciences. It's the operation of 2 medium-scale devices. The one on the left we call Big Red Ball. I'll show you a little bit more about that. It's a spherical plasma containment device. And the one on the right is the Madison Symmetric Torus, which is a toroidal device. The experiments that we conduct using these 2 devices are aimed primarily to understand energy flows between fields, both magnetic field and electric field, within the plasma and the particles in the plasma. This is a really important topic, both for the astrophysical natural plasma setting as well as for the fusion setting in the laboratory. We also are engaged in fusion topics that are specific topics in both tokamak magnetic confinement and reverse field pinch magnetic confinement. Those are two flavors of magnetic toroidal magnetic configurations that we can study on the MST. And this facility, one of the things about it is that's important is that we're funded in part to support external users who would propose experiments and then come to Madison, work with us to do experiments that they lead. But a big part of the program is the UW Home Team Program. So some of the funding that we get for this is to support our experiments for our own ideas, and that includes graduate student work. So this is the Big Red Ball and the MST. If you were in Madison in person, what we would do almost immediately when we were talking about these facilities is take you and stand in front of some windows where you can look at these two facilities and we can talk about that. Of course, that's more difficult to do virtually, but I can show you a few experiments. Actually, first, what I want to do is mention one of the capabilities within the Big Red Ball. This is an example of the kind of experiment that we do. It's magnetic reconnection studies, and it's a particular configuration we call the terrestrial reconnection experiment, or TREX for short. The Big Red Ball is two hemispheres and it can be separated and we can get inside relatively easily. And this coil set that you see next to the Big Red Ball gets inserted inside the device. And these coils are energized in such a way as to cause the process of magnetic reconnection to occur. And so there are two running short movies of magnetic reconnection on the left. Magnetic reconnection is magnetic field lines coming together, snapping, if you will, breaking and pulling apart. It's a really important process in both natural plasmas and in the fusion context. And one of the reasons why it's so important is that it can energize particles to very high energies. So that's what's shown in the bottom picture is spiraling particle orbits along the magnetic field lines in the Earth's magnetosphere, just as an illustration. Here's a kind of a close-up picture of the Big Red Ball. Don't have a person in here to scale, but it's a meter in radius, so a couple meters in diameter to give you some scale. And what you're looking at is the outer surface of it. There are some tracks that you can see that are aluminum. These are holding coils, which are there to create a magnetic field, which we can apply to the plasma. Then there are power supplies and diagnostics and whatnot surrounding the device. This is a picture underneath that shows a close-up of one of the race tracks that's holding one of the magnet windings to create the magnetic field. I also picked this photo because you can see this kind of rough, foamy looking surface to the device itself. This is an insulating material, is all that it is. It helps keep the device both warm and cold at a constant temperature. And it's painted badger red. I'm wearing the badger red today just for fun. And that's what has given this device its name. The Big Red Ball is simply that it's a ball painted red. Here's a picture of MST sitting in the high bay. This is a bit of an older picture with at a moment when we had a lot of the equipment pulled away from the device. And that's good from the point of view of being able to see what the device is, because you can see the torus sitting in the middle. Now, if you look at from the same angle, it's full of equipment surrounding it. Here's a picture from above. One of the reasons I like showing this picture is it illustrates some of the diagnostics that we have on this device and representative of the kinds of diagnostics that we use on our devices more generally. Our facilities create plasmas, which are pretty hot. MST plasmas can get up to, in the electron volt unit, up into the 2 kilovolt range, so that's pretty hot. Nevertheless, we can use diagnostics as simple as little pieces of wire or little loops of coil stuck into the surface of the plasma. They can survive there. But many of our diagnostics are more sophisticated than that, based on lasers or particle beams, or we look at the radiation that naturally comes from a small amount of what we would call impurity ions in the plasmas. We almost always work with hydrogen or helium plasmas, but there's always a little bit of oxygen left from the remnant water and air. And there's also the material surroundings. So in this case, the MST vessel is aluminum, so there's always a little bit of aluminum sitting around. Here's a picture of a graduate student sitting in the MST control room. This is what the normal setting would look like for experiments that we do. So one of the reasons I wanted to show this was to emphasize the opportunity for graduate students to engage in our experimental activities. These are very hands-on facilities. One of the things that we always emphasize for prospective graduate students is you get a grounding in experimental plasma physics from the ground up, so to speak. You operate the device, you operate the diagnostics, you help maintain, you learn about the vacuum, you learn about high voltage, you learn about power supplies, and of course, all of the other things having to do with data analysis. So this is a typical setting for one of our experimental days. We also have a new facility, which is under construction. It's called the Wisconsin HTS, High Temperature Superconductor is what that stands for, Axisymmetric Mirror, or WHAM for short. This is a new project which is funded by a different branch of the Department of Energy, ARPA-E. And this project, its goals are to develop the axisymmetric mirror, which is a long configuration with strong magnetic fields at the end rather than a toroidal configuration, to develop this mirror concept for use as a fusion neutron source. And one of the things that's going to happen with this facility is to leverage new technologies, most importantly, high temperature superconducting technology to confine a fusion producing plasma. HTS magnets are important in part because they can operate at high temperature, but from the fusion point of view, we're more excited about their ability to access very high field. You can get to 20 Tesla plus with high temperature superconductors, whereas for standard superconducting technology, the typical limit is about half that or maybe even a third of that. The other thing that's going to happen is to employ some novel plasma heating methods. So there's a cartoon drawing of the facility, the way it's going to look up in the right-hand corner. It's axial, so it has a cylindrical-like symmetry with these strong magnetic fields at the end. You can't quite see all of that detail there. It's located in a big room at what's called the Physical Sciences Laboratory. It's one of the laboratories available to University of Wisconsin. You can see there is equipment there being collected. Here's a little bit more clear view of the room space in which it's going. So at the moment, this is in an assembly project phase. This is always a good time for students to be involved in research because you get in right from the beginning of what's going on. And Professor Forrest, who is leading this, is definitely interested in having graduate students work on this project. In addition to our own facilities that we operate here at Wisconsin, which we're very proud of and we think are very important for the reasons that I've said, most importantly, it's a way to have hands-on research as part of your graduate education. But we also have research collaborations on larger fusion facilities around the world. Several of them are shown here. We have projects on the D3D facility at General Atomics in San Diego. This is the largest fusion facility here in the US. We also have collaborations at NSTXU, which is located at Princeton Plasma Physics Laboratory. And there are burgeoning new opportunities for facilities elsewhere in the world. So one of them is the brand new JT60SA in Japan. This is the world's largest now beginning operations superconducting tokamak facility. It's a little bit smaller than ITER, but it's designed to produce longer pulses than ITER will. You can see the people in each of these to give you some scale. And the kind of activities that we have are to study what are called disruptions. This is an important process in toroidal plasmas where the plasma can suddenly terminate itself due to large-scale instabilities. So this is something that we're studying on D3D, as well as self-generated plasma current, which might be important for some fusion scenarios that are attractive. We have neutral beam injection and radio frequency heating experiments on a smaller device located at PPPL. And we have collaborators that we're working with on, as just an example, energy resolving X-ray cameras, which could be used on JT60SA. They're already used and being developed on MST, but they could be deployed elsewhere in the world, for example, JT60SA and others around the world. With that, I'll turn it over to Jeff. And I want to add just a couple remarks about Jeff. We're very excited to have Jeff. Jeff just joined our faculty here at Wisconsin this past year, right at the beginning, basically, of the pandemic. And so, like everybody else who's had to work under unusual circumstances, Jeff's first time here has been strongly affected by the fact that we haven't all been able to be working together. But we're really excited to have Jeff, so I'll let him describe our theoretical and computational plasma physics program.
Thank you, John. So I'll speak on the theoretical and computational side. Now this is broadly split into two categories: fusion plasma research and plasma astrophysics research. I will say that we pride ourselves here at having strong programs in both theory and computation. So it's important to have both a theoretical physical insight as well as very capable numerical simulations. And combining those is a real strength of our program. On the fusion side, I'll just describe very briefly a couple of activities. So for example, Professor Terry is heavily involved in turbulence and transport research in magnetic fusion plasmas, particularly tokamaks and stellarators. And these can range from relatively simple simulations that you might even be able to do on a laptop or desktop to understand basic properties, up to very massively parallel gyrokinetic simulations that may run on thousands or even tens of thousands of cores or a comparable number of GPUs. And this figure here that you see in the top is from a gyrokinetic simulation. An area of research that I'm interested in here at the bottom is topological edge waves in fusion and basic plasmas, which is analogous to an area of study that came out of condensed matter physics. There's also a strong interest in plasma astrophysics research here in the department, and this includes a variety of topics, including solar wind, MHD turbulence, magnetic dynamos, magnetic reconnection, particle heating and acceleration, and a variety of other topics in astrophysical plasmas. This figure on the bottom here, for example, is showing an analogy between something that Professor Boldarev is studying, the expanding of the magnetic field lines in the solar wind escaping the sun, which may be analogous to the expansion of magnetic field lines in the edge of a magnetic mirror confinement device.
Thanks, Jeff. Let me just add something that Jeff didn't mention that I think is really important, and it's a hallmark feature of our program. The theoretical and computational efforts are often very closely aligned with the experimental efforts. And so these two cartoons, these two pictures at the bottom illustrate this opportunity. So there's this magnetic field expanding from the sun, and we have this new mirror experiment, and the nozzle coming out of the end of the mirror has a commonality in its geometry. And so there may be an opportunity here using the laboratory setting to understand this natural setting. Of course, we do this in a collaborative way. One of the large themes that we work on is plasma turbulence. And so we have strong collaborations, both between the experimentalists and theorists, but a diverse program as well, looking at many different things. Here at Wisconsin, in addition to the activities that we have here in the physics department, there's a large campus community doing lots of different things. One of the important ones is astronomy. So I mentioned at the beginning, Professor Zweibel, who has a joint appointment with us. And that's been a strong collaboration, again, even on the experimental front. I want to emphasize that one. And I also want to emphasize the context. What you're looking at is some work that Ellen Zweibel has done with her collaborators, looking at turbulence, magnetized turbulence in particular, coupled to cosmic rays, driven by cosmic rays. Ellen Zweibel is one of the world's experts in cosmic rays. And so this again just emphasizes this common connection of picking plasma problems where magnetic field have a large role and making a connection. Cosmic rays are rather important in the universe. They carry a lot of energy, and probably the only way that they can get energized the way they do is within the plasma setting where you can have very large electric fields. So understanding that is really important. Beyond astronomy, within the engineering campus here at Wisconsin, we have close collaborations with engineering physics and electrical and computer engineering. So these are just pictures representing this. In the bottom left-hand corner is examples of advanced computational modeling, again in a toroidal geometry, which makes it clear that this is a magnetically confined kind of context. Next to it is a picture that represents fusion technology. What do fusion reactors of the future look like? One of the things that happens on campus is to understand that. And then we also have other experimental facilities on campus. On the top, shown on the right, is the helically symmetric stellarator, HSX. And at the bottom right, the Pegasus spherical tokamak. So these are devices that we work with our colleagues on campus to understand fusion in a much broader way. One of the things we're really eager to have on campus is a next step version of the stellarator based on quasi-symmetry, which is one of the important concepts that have been developed here at Wisconsin. And so we're working collectively, collaboratively on campus to do that. The WAM project, by the way, is also very collaborative across campus. Okay, we're almost done here. So I just wanted to indicate that one of the things that's special about our program here at Wisconsin is that we have a very highly developed plasma course curriculum. I think probably one of the best course curricula in plasma science in the world, literally. So here's a list of the courses that we have, starting from introduction to plasma physics, going systematically through, rigorously through different plasma processes, waves and instabilities, plasma kinetic theory, et cetera, to magnetohydrodynamics. And then we almost always offer every year at least special topics classes, like for example, this semester or last semester, I guess it was, Professor Terry, who's a world expert in plasma turbulence, gave a course on turbulence, which is a basis for a book that he has been working on plasma turbulence. And if you come to Wisconsin, if you're somebody who's listening to this, you're a prospective student and you come to Wisconsin, you may be interested in plasma, but you're not quite sure. I want to call your attention to the seminar series that we have that are noon on Mondays. This is open to anybody. Maybe by the fall, we'll be back in person. So these are commonly held within the physics department, so they're pretty easy access for students.
So thank you very much for listening. We are delighted that you are interested in plasma research and the PhD program here at UW in the Department of Physics, and we really look forward to meeting with you.